When you think of multi-robot object transportation, you probably picture warehouse automation systems moving standardized pallets or shelves. Those systems work because the robots and the objects are perfectly matched. But what happens when you need to move a real-world object? Something with an irregular shape, a shifting center of mass, or no predefined lifting interface. The bottleneck isn't navigation. It's the formation phase. Before any robot can lift or push, the team must autonomously position itself underneath the object to create a stable, load-bearing structure. And doing that while balancing non-uniform weight distribution in a cluttered environment is a notoriously hard control problem. Traditional approaches usually rely on predefined target formations, uniform mass assumptions, or explicit mechanical attachments. Some methods use potential fields or geometric optimization to distribute robots evenly across an object's footprint. But geometric uniformity doesn't equal load uniformity. If an object's center of mass is offset, a geometrically even formation will tip, overload certain robots, or fail entirely. The research community has largely focused on navigation during transport, leaving the initial pattern formation under arbitrary mass distributions largely unaddressed. A recent study tackles this head-on by framing the formation problem as a partially observable multi-agent reinforcement learning task. The goal is simple in concept but complex in execution. Train a team of robots to self-organize under a hovering object, avoid obstacles, and converge on a formation that naturally balances the load. They achieve this using a centralized training, decentralized execution paradigm with a multi-agent proximal policy optimization algorithm. Let's break down exactly how they modeled the problem, computed load distribution, and designed the reward structure to make it work. The environment is modeled as a partially observable Markov game. Each robot operates with local observations, which is crucial for scalability. The observation vector for each agent is highly structured. It includes the robot's own position, velocity, and current estimated load. It also includes relative positions and load estimates for all nearby teammates. For environmental awareness, each robot uses a synthetic LiDAR setup to measure distances to static obstacles and to the boundary of the target object's footprint. But the key innovation is the load similarity score. This is an aggregated metric that tells each agent how close the entire team is to achieving a perfectly balanced load distribution. Now, how do they actually compute the load each robot should carry? They treat it as a static equilibrium problem. Only robots inside the object's footprint participate. For those robots, they calculate the relative vector to the object's center of mass. Then they enforce two physical constraints. The sum of all individual loads must equal the total object weight, and the sum of the moments around the center of mass must be 0. This creates a linear system of equations. Depending on the number of robots inside the footprint, they solve it using either least squares regression or the Moore-Penrose pseudo-inverse. The resulting load vector is normalized and padded with zeros for robots outside the footprint. They then compare this actual load distribution to an ideal uniform distribution using cosine similarity. This similarity score becomes the core of their reward function. The reward function is a weighted combination of 4 components. First, a positional reward that guides robots into the object's footprint. Second, a collision penalty to keep them safe. Third, the load-sharing reward, which directly scales with that cosine similarity score. Fourth, a success bonus triggered when all robots are inside the footprint, and the load similarity exceeds a dynamically calculated threshold. That threshold isn't arbitrary. It's derived from the maximum allowable load difference between any 2 robots. The math accounts for edge cases, like when one robot carries maximum load and the rest carry minimum, ensuring the threshold adapts to the team size and physical constraints. For policy optimization, they use MAPPO. The architecture follows a shared parameter approach. Each robot runs an identical stochastic policy, implemented as a 3-layer MLP, with RayLU activations. The actor outputs the parameters of a diagonal Gaussian policy, which is then squashed through a tan function to respect velocity bounds. During training, a centralized critic receives the concatenated observations of the entire team. This critic computes state value estimates for each robot, enabling generalized advantage estimation. This CTDE setup gives the learning process global information to converge faster, while the deployed policies remain fully decentralized and scalable to larger swarms. The researchers tested this across 5 environments of increasing complexity. You start with a simple object in an empty space, then add cluttered obstacles, introduce non-uniform mass distributions by shifting the center of mass, and finally add geometric cavities. They scaled the team from 3 to 20 robots. The results show robust generalization. Success rates remain high across the first 4 environments, even with shifting mass and tight passages. Execution steps decrease as team size increases, thanks to the redundancy and load distribution. When compared to baselines like random initialization and a dynamic uniform distribution combined with expectation maximization, the learned policy significantly outperforms them. The baselines optimize for geometric spacing, but they fail to compensate for asymmetric mass. The learned formations, on the other hand, closely approximate mixed-integer linear programming optimal solutions, proving that the network implicitly learned the underlying load balancing physics. This work demonstrates that load-aware formation control doesn't require explicit physical modeling or predefined templates. By baking static equilibrium constraints into the observation and reward structure, multi-agent reinforcement learning can autonomously discover stable, scalable support formations. The policies generalize across cluttered scenes, arbitrary geometries, and varying team sizes. Future iterations will likely focus on extending this to full transport execution after lifting, adding onboard estimation for unknown object mass and geometry, and exploring graph-based policy architectures to handle even larger robot swarms. If you're working on cooperative manipulation or decentralized control, the way they bridge physical constraints with deep learning is a strong blueprint for what's next in multi-robot systems.